So for this next problem, we've got a structural fixing. So we've got a angle bracket or a steel bracket that's screwed into the wall, and we've got two tension members. So these will be angle members, and they're in tension, so they're getting stretched. And one of them's got a force of 60 kilonewtons on it. So I'm thinking to myself, well, that's an equivalent to the weight of something that's got a mass of 6 tons. And this is about 8 tons of force pulling on the other structural member. And so if we were designing these bolts or figuring out whether the capacity is enough for these bolts, what we want to do is to find the resultant vector and its direction. Now, you can see at the moment when they've drawn this problem, they haven't drawn both of these forces at the same point, so you can't really see the triangle there. What you can do with forces, and we'll explain why a little bit more later in the course when we start looking at equilibrium and rigid bodies, but for now, what you can say is if you take the line of action of the force, so that's the same as the direction of the force, and you can trace that back. You can do the same thing with the other force. You can trace that back. And what you can then do is you won't change anything if you move the force vectors along their line of action. So I can move this back along here. It won't change anything in terms of the analysis of that plate. And I can do the same with the 60 kilonewton force. Move that back along its line of action until we get those two forces joined up, and so, or acting on the same point. I won't go too much more into that at the moment. We'll talk about that a bit later when we look at rigid bodies, but just know that you can do that in order to get these forces to all act on the same point. So then what we'll do is we'll just draw this again without the bracket in the background. So we've got 13 degrees, and again, I'm always doing this to scale just so that I can check my answers, and even if you don't do it exactly to scale, if you do it roughly to scale. So we've got 60 kilonewtons. I'll just do one division. It's going to be a little bit long, so maybe just try, let's just see where we end up. Let me do my components in red. So 10, 20, 30, 40, 50, 60. So we're just doing 5 divisions is 10 kilonewtons. This one's at 47 degrees. And we're going 80 kilonewtons. 10, 20, 30, 40, 50, 60, 70, 80. Okay, we'll just add the direction that those are going in. So we're trying to combine these vectors to get the resultant force, or to combine these two forces to get the resultant force. Better just put on all the information we've got. So we know that this is 13 degrees. This here is 47 degrees. Now, if we wanted to combine these vectors, this time they're not x and y components, but just see the best way to show this. We can still use that same rule. It's always the case. You put for any vector, you put the vectors nose to tail. And so we could take this vector and put it here. I'll just do it roughly for now. And then if we join the start point to the finish point, you're going to get the resultant vector. So that would be the resultant vector here. Alternatively, let's just move all that back again. You could have done the same thing with the other vector. Oops, excuse me. So we could have done the same thing with the other vector. So we could have taken this one. We could join that nose to tail with this one. So moving up here, so it stays parallel. And we would have got exactly the same vector. So the resultant would have been through here. Oops. The resultant vector would have been through here. we don't really want to. So this time you'll see when I've moved that force vector, I'm not moving it along its line of force, I'm moving it parallel to that. And we don't really want to do that because it just confuses people and makes it look like that force is acting somewhere else. So rather than do that, we just imagine moving them nose to tail. And so imagine, take this vector, keep it parallel, move it across to here, keep it the same length. Just draw a dotted line there, in red probably. Do the same with the other one. Across here. And so this time you're getting a parallelogram rather than a rectangle because the component vectors were not at right angles to each other. So the resultant vector is going to be somewhere here. Unfortunately, it's going to cut through my angle, but we'll fix that later. Okay, just to show that just move this 47 out the way a little bit, this angle, just to show that that angle is not showing. I don't know why it keeps doing that. So just to show that that angle is not showing the angle from here to the black line, what we'll do is we'll just put the arrows on the end just to show it's going the whole way. I'm not showing a direction on my resultant yet. Another thing I haven't done yet is so what we're going to do is, we could get the answer from that, so let's just have a look at roughly what the answer is. I'm just going to write this at the side, it's just a rough calc, so you've got 10, 20, 30, 40, 50, so I'll show you what I'm doing, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, so it might be about 124 probably. So it looks like from the scale drawn, we're getting something like 124 kilonewtons. And it's acting at an angle of approximately 22 degrees. Okay, so that's just what we're going to use to check our answer. So what you could do to solve this is use some other trig rules that I haven't presented to you. If you remember those from school, you can go ahead and use them. Sometimes they're quicker. But what always works is to break these down into their x and y components and then use the x and y components, add those together, and then use those combined x and y to find out the resultant. So let's have a look at where those x and y components are. So we can't use, so I just should explain, the reason we can't use this directly is because this triangle here or this triangle here, neither of those have a right angle in them. So we can't use sine, cos, and tan, or SOHCAHTOA, and we can't use Pythagoras rule because we don't have a right angled triangle. Still a few things I need to add to my diagram. So this was 60 kilonewtons, and this one here was 80 kilonewtons. Okay, should have thought ahead. It's going to get in my way. I'm going to move it over here. So let's figure out where those x and y components are. So for this first vector, better just draw on my x and y axes, just so that anyone looking at it's in no doubt about what I've assumed for x and y. So I'll do x horizontal, y vertical as shown on the page. Or if you're on plan, I suppose x is east and y is north. Okay, so for this first vector here, so I'm going to go down here. Let me draw my x and y components. So y is going this way, and already I'm thinking about the direction of these x and y components. Just draw it solid. So this is going negative. We'll call this 1. We'll call the force F, I reckon. So we'll call this, the combined one's just going to be F. We'll call that, doesn't really matter. We'll call this Fx1. Oh, not Fx1, sorry. So that's in the y direction. So Fy1, Fx1. Okay, and then we're going to follow the nose to tail. So we're going to come down this vector and then go up this imaginary vector. Imagine moving it nose to tail. So we're going to imagine we're then going up here. So this vector moved nose to tail. This one is to here. To here. Just fix up some colors a little bit. We'll call this F, now that's X direction, it's going to be negative, that one, Fx2 and Fy2. So let's calculate. Now we need to have a think about what angles we've got inside these triangles. So at the moment, we know that this the angle from here to here is 47 degrees. And so if we take this angle here, you can see that they make a right angle. So you've got a right angle where I'm tracing out with the cursor here. So there's a right angle there. And so this angle plus this angle must add up to 90. So this one here must be 43 degrees. Okay, now we've got to find an angle in this little triangle down here. Well, this is horizontal to this angle, so to this line here. That's exactly the same as horizontal to that second vector. And these two things are parallel, so that must also be 13 degrees. So this here must be 13 degrees. That comes back to your angles rules. So one of the angles rules, let me just do a very rough sketch. If you've got one line, another parallel line, so usually you show they're parallel, but just putting a bit of an arrow on them, it's almost like a vector. If you've got another line crossing these, this angle here is always equal to this angle here. This angle is the same as that angle, and that works for all of them. So you might have this angle equal to that angle, and actually these two angles opposite each other are also equal. And so if you've got two parallel lines with another line crossing them, you can find out other angles just from that rule. Now the other thing, so the angles that I've marked all the same are the same. The other thing is these two angles and these two angles add up to 180 degrees. So they're called complementary. And you can see why. It's because these two here must add up to 180 degrees, and this one is the same as that one. Okay, so that's all your angles rules. I'm sure you've done that at school. If you're not sure about any of that, just have a look online and do some more reading about it and do some practice. But anyway, we've now got one angle in each of these. We've got a length on this side. That was 80 kilonewtons. I've turned it black at some point. We don't have a length on this side yet, but we know it's basically this vector moved nose to tail. And so that must also be 60 kilonewtons. The length of that line must represent a magnitude of 60 kilonewtons. So let's start working through these now. So we've got, we'll keep doing it for now, the sine, cos and tan, and putting on the labels on the sides. So we've got this must be the hypotenuse, this must be opposite, this must be adjacent. For this one here, your right angles here, right angles here. So this must be hypotenuse, This must be opposite, this must be adjacent. If we need to use Pythagoras, we'll stick those on again or as well in a minute. I'm just going to shuffle this to the side a little bit. Okay, so let's start working through those calcs. We'll get fx1 first. So for fx1, we've got the hypotenuse, we want the opposite, so sine 43 degrees is equal to opposite over hypotenuse, which is equal to, so sine 43 degrees equals opposite fx1 over hypotenuse is 80. So therefore, fx1 times both sides by 80 is 80 sine 43 degrees. So that's going to be equal to, let's get the calculator. So it's 80 times sine 43 degrees. .56. I'll keep the four significant figures for now, because what we'll do, we'll be combining these, so we want to keep it pretty accurate for now. So 54.56 kilonewtons seems reasonable. Now this is 43 degrees. If that was 45 degrees, these would be the same. But because it's 43 degrees, they should be pretty close, but Fy1 should be just a little bit bigger because this is just a little bit shorter, so that angle's a little bit smaller. So I'm just doing checks as we go along. So let's do the other one. So y now, so we've got the hypotenuse still, and it's the adjacent, so we're using cos. Cos 43 degrees equals Fy1 over 80. Just a bit of a short, so Fy1 is equal to 80 times cos 43 degrees. Back to our calculator. And what we'll do is we'll just change it there. Or will I? Get to the end. So 58.51. Does that agree with what we're saying? So this is less than 45, so that one should be smaller than that one, but they should be pretty close, and that's exactly what we've got there. So it looks like we've got the right answers for that one. Okay, moving on to this second triangle now. So first we'll find x again. We've got the angle, we want adjacent, we've got hypotenuse, so this time we need to use cos to get the x value. And you'll see again, not always the case you use cos for x, just depends which angle you're able to figure out. So it's always worth writing out. So therefore, cos 13 degrees is equal to adjacent over hypotenuse. So cos 13 degrees is equal to fx2 divided by 60. So fx2 is equal to times both sides by 60. 60 cos 13 degrees, which equals, so 60 times cos 13 degrees, 58.46. Look reasonable. Well, on my scale drawing, those two are pretty similar size, so yep, looks reasonable. Let's move it up a little bit. And now we've got Fy2 to figure out. So opposite hypotenuse sine. So sine 13 degrees equals opposite over hypotenuse. So sine 13 degrees is equal to Fy2 divided by 60. So Fy2 is equal to 60 sine 13 degrees. Same thing. Oh, so sine 13 degrees. 13.5. I'm just going to check that it's such a round number is kind of interesting. Just because it rounded up that way. Kilonewtons. Okay, so now we've got all the x and y components, and so we're just thinking to ourselves, if we want to get this resultant vector, we can just add up all the x, and so add the y components, add the x components, and we can find the x and y components of f. So I guess I'll just quickly sketch that, just so you can see what's going on. So we're taking this vector here. I'm not going to draw this to scale, I'm just going to do it roughly. So we've got f like so. And we're going to come down by fy1. So that's this one here. So down fy1, and then we're going to come up by fy2. And then we're going to go negative now, just thinking about what I've done here. So we'll just go back through all this. So let's think about the signs on these. So far I've just calculated magnitudes, but we need to be careful with our signs when we're doing this stuff. So we've got fy1, so let's just go through the x1 is negative. So fx1 is negative, so that should be negative, that should be negative, that should be negative. Fy1 is also negative. Negative, negative, negative. Your x1 and yep, that's right. X2 is also negative, and then Y2 is the only positive. So that just stays as is. We'll put the negatives down through here. Okay. And so your X total, or F total, so yeah, F, let's just call it Fx. So Fx is just the sum of those two X components. Fy is coming down here, and Fy is basically this negative, and then you come back a bit, so you got a positive and brings it back to Fy. So let's find those. I'll just move the page up again. So Fx is equal to f of x1 plus fx2, not f of x, fx2, which is equal to, just missed out one negative in there, negative 54.56, negative 58.46. So we're taking fx1, fx2, both of them are negative, so it's going to be a big negative number. So we're going to do negative 54.56, negative 58.46. Just want to see if this, yep, that's all good. So negative 113.02. We'll just keep four significant figures, so negative 113. Kilonewtons. Going to have to move up again. Fy is equal to Fy1 plus Fy2. which is equal to, so Fy1 was negative 58.51, so negative 58.51 negative y2, so it's not negative this time, we're going back up the way, so it's plus 13.5, which equals negative 58.51 plus 13.5 is negative 45.01. Try and make that actually look like a negative. Just double check that. 45.01, that's all good. Seems sensible, yep. So we've added about 50 to about 50, so we've got minus roughly about 100, so a bit more. And then for this one, we've got negative 58, but then we're going to add 13.5, so it looks sensible. Okay, so now we've got these two, we now know what this one equals. And we know what that one equals. And so we want to find the resultant force. So to get its magnitude, we can just use Pythagoras. You'll all know this by now, but I'm just thinking there's my right angle, that's opposite. So this is going to be the hypotenuse. And then, well, we're on Pythagoras now, I guess. So we should call that C. And then A and B don't really matter, AB. So Pythagoras says C squared equals A squared plus B squared. In our case, that's F equals Fx squared plus Fy squared. It doesn't say that, it says F squared equals those. And so to get F, you need to take the square root. Of those, which is equal to the square root of, nice, 113 squared. Now you don't really need to write the negative in there. When you square a negative, you get a positive. Let's check that. So the square root of, as I say, you don't really need to write the negative. Square a negative, you get a positive. $121.63. Is the magnitude. Let's go back to our 124, near enough. A little bit high. I think it'll just be inaccuracies in my sketch. And let's round that to three significant figures now. So it's 121.6 kilo, three significant figures. So 122 kilonewtons. So we've got the magnitude. Now we need to find the direction. So we'll come back up here. I've got to decide where I'm going to take my direction from. I don't think the question told me. Determine the resultant and its direction. So it just wants us to find a direction. Sometimes for this problem it might ask you to find the direction from one of these members. What we'll do is just the usual, where you're taken from the x-axis. In this case, because we're heading this way, it might be sensible to take that relative to the negative x-axis rather than taking it from the positive, because you're looking at this direction here. And it might even have been more sensible for me, if I'd thought a bit more carefully, it might have been more sensible to do my x and y axes like this, so that positive was in this direction and positive y in that direction, just so that I didn't get all these negative numbers. But anyway, too late now. and it doesn't change, like it doesn't make the answer wrong, it just would have made it a bit tidier. Okay, so we'll find it relative to the negative x-axis, and so probably the best angle to use would be this angle here, because then I can use my angle rules. This is the negative x-axis up here. That angle is going to be the same as that angle. So we're coming back to that same rule again. I don't really need the ruler. So if you've got two parallel lines and a line crossing, there's the Z rule. So this angle here is identical to that angle there. Or you could say this angle here is identical to that angle there. So all of these little rules are useful when you're working with this type of problem. So we are going to call, what will I call this? I'll call this theta. Okay, now let's just think about whether we're using sine, cos, and tan. We'll probably just use these two sides. There's my angle, there's my hypotenuse, so this is going to be opposite, this is going to be adjacent, so we'll use tan. So we're going to have tan theta is opposite over adjacent, which in our case is minus 45.01 divided by minus 113. Those negatives are just going to cancel out. I'm writing on my negatives this time. Sometimes it actually makes a little bit more sense if you just say, look, the arrows are telling me what direction, so I don't need the negative in there. So we'll just say 45.01 divided by 113. Just looking at that now, let's just get this to three significant figures as well, just to keep all this tidy. 45.0 divided by 113. Just have to move this up again, so I've got space to write. So therefore theta, you just need to do the inverse tan of the other side, is tan to the minus 1, 45 divided by 113, which is equal to, okay, again, a tan for this little calculator, 45 divided by 113. Sorry, 21.71 degrees. Three significant figures. So we know this angle is 21.71, which means this angle is 21.71, and that is heading anti-clockwise from the negative x-axis. So force has magnitude (122 kilonewtons), and that's at 21.7 degrees anti-clockwise from the negative x-axis. Okay, so that's a problem combining two force vectors. I'll try and speed it up a little bit for the next one, which is going to be a problem solving three force vectors. Same process. We'll try and find some ways to cut down how much you need to write. We'll have a go at that one.